All right, so welcome everybody. So we are delighted to host Professor Luca Carlone from MIT as part of this seminar. So let me briefly introduce Luca. So Luca is a Leonardo Career Development Associate Professor at MIT in the Department of Aeronautics and Astronautics. And he is also a principal investigator in LEADS, the Laboratory for Information Decision Systems at MIT. He has a quite long bio that I won't read in full, I think, but just a few highlights. He received his PhD from the Polytechnic University of Turin in 2012. He joined LEADS as a postdoctoral associate in 2015 and became a research scientist in 2016. And before that, he spent 2 years as a postdoc at Georgia Tech between 2013 and 15, where we actually collaborated. And his research interests include nonlinear estimation, numerical and distributed optimization, probabilistic inference, applied to sensing, perception, and decision-making in single and multi-orbit systems. He's made quite a few seminal contributions to the robotics in general field. He has won different awards. Just to mention a few, just recently he got awarded, his group got awarded by a Best Student Paper Award at IROS 2021, Best Paper Award in Robot Vision at ICRA 2020. And the list is quite long, so I won't read it in full. It includes also Best Paper Award at WAFER 2016 and etc. much more. He is also recipient of the NSF Career Award in 2021 and RSS Early Career Award in 2020 and more. At MIT, he teaches the Robotics Science and Systems course, which stands for RSS, but not the conference actually. And he also, and this is an undergraduate course, and he also introduced and created a graduate level course on visual navigation for autonomous vehicles, where he focuses on mathematical foundations along with fast C++ implementations. So Luca, we are very much delighted to have you here and looking forward to the talk. The floor is yours. Thanks.
Thank you so much for the kind introduction. It's really a pleasure to be virtually here, and I really hope to visit at some point in person sometime soon. So at this point, you should be able to hear me. Hopefully, you will also see me.
Yeah.
See my screen. Okay, just 1 second to fight a little bit with Zoom. Okay. I think that seems to be mostly working out. Okay. Okay, again, it's a great pleasure to be virtually here. As Vadim said, I'm Luca Carlone. I'm an associate professor at MIT. And the plan for today is to tell you about the work of my group going from SLAM, which is simultaneous localization and mapping, to real-time scene understanding for robotics. And I really want to cover these two big ideas that we have been working on. The first one is the notion of 3D dynamic scene graphs. And the second one is the idea of certifiable perception algorithms. But maybe a good way to start is just to give you a one-slide overview of the work we do in my lab. At MIT, I'm the director of the SPARC lab. SPARC stands for Sensing, Perception, Autonomy, and Robot Kinetics. And of course, we work in the broad area of robotics and autonomous systems, but we have a specific focus on robot perception and vision-based navigation. So the research areas in my group are the ones that you see along the columns of this slide. We have work on robust and certifiable perception. It's really about robustness of vision-based navigation, SLAM, and object pose and shape estimation. And I'm going to touch on these topics at the very end of this presentation. We have a research area on high-level scene understanding, or what people in robotics are calling spatial AI. And you're going to hear quite a bit about this during today's talk. And finally, we have a research line on co-design. Co-design is really research happening at the intersection between perception and other areas of robotics, including control, communication, mechanical design. It's an area that unfortunately I don't talk too much about during this presentation, but I'm super excited about it. For example, the work that you see here at the bottom on soft area manipulation is the one that Vadim mentioned, won the Best Student Paper Award at IROS this year. Okay, so this is the research in the lab. The plan for today is to really cover 3 topics. I want to tell you about Chimera, which is an effort in going from SLAM to 3D metric semantic mapping. Then I want to tell you about 3D dynamic scene graphs, which is about going from metric semantic mapping to high-level understanding. And if time allows, I want to cover the idea of certifiable perception algorithms with some focus on object pose estimation. This being said, along the talk, if you have questions, feel free to just interrupt me or ask questions and let me know if the video is not smooth or the audio is not smooth, such that I can fix things on my side. Okay, so we're going to start with Chimera. Maybe a good way to start is to tell you, what is a basic motivation for us to look into high-level scene understanding? Well, a motivation behind a lot of research we do in my group is really the realization that there is still a large gap separating robot perception from human perception. With robot perception, we made impressive progress in SLAM, simultaneous localization and mapping. And indeed, right now we have good algorithms and implementations which are able to create a sparse or dense point cloud map. And these kind of maps can be built in real time on a robot using cameras or other sensors. Other works, such as the pioneering work on SLAM++ from Andrew Davison, is able to build a map in the form of a collection of objects. But in general, with simultaneous localization and mapping, we're quite good. We have good algorithms to build geometric maps of geometric primitives, including map of points, lines, voxels, meshes, and so on. This kind of geometric understanding is what I'm going to call the SLAM comfort zone. However, to convince you that human perception is much more than that, I probably just have to show you a single image. Okay, so it's the single image that I'm showing you on the right of this slide. By looking at this image for a few seconds, as a human, you can easily understand the geometry of the scene picture in this image. For example, you can understand that there is a road, there are buildings, right? You can understand what is the semantics of the scene. You can detect that there are cars, pedestrians, maybe yellow cars are taxis. And you can even reason over relations among different objects. For example, one car can be following the other, or maybe a pedestrian is trying to cross the street. This kind of holistic high-level understanding of the scene that we can easily afford as humans is still out of reach for our robots. A lot of work I'm going to present today is about bridging this gap. But before we get there, let me tell you about why high-level understanding is so important for robotics. First of all, high-level understanding is key to interaction. If a robot is just able to understand the geometry of the scene, we are doomed to issue commands, low-level instruction. For example, robot, go to position X, Y, and Z. The robot will understand this command because we'll have some geometric understanding of the environment. But personally, in the future, I would like for my robot to be able to execute high-level instructions. For example, I want to tell my robot, go grab me the cup of coffee on the table in the kitchen. And in order to parse and execute this kind of instruction, the robot will need to understand semantics. For example, we'll need to understand what is a cup of coffee, what is the table, what is the kitchen. We need to understand geometry in order to be able to plan a path from the current location to the kitchen. And we need to be able to understand relations. What does it mean for the cup of coffee to be on the table or for the table to be in the kitchen? So high-level understanding is key to interaction with humans. Moreover, high-level understanding is also key to robustness. And I'm going to convince you that this is the case with the slides I really like. So of course, if I show you this slide, as a human, you can easily detect the car in this slide. But if I show you the full picture from which I cropped the shape of the car, you can stare at the picture for a few seconds, and then you can realize that actually in this picture, there is no car. There is a white van, and then the car is just painted on the van. And your mental process in understanding this scene has been probably like the following. You detected the ground, you detected the car, you detected the van, and then you reasoned on the fact that physically the car and the van cannot be on top of each other, cannot be at the physically same location. Therefore, the car must be painted on the van. So in other words, what I'm saying is that robust perception for humans relies on simultaneously understanding geometry, semantics, physics, and relations in 3D. And a lot of the work I'm going to present today is about trying to capture these aspects for our robots. So the first part of the presentation is going to cover how to capture and understand geometry and semantics in 3D for robots. The second part is going to talk about relations in 3D. So the first part of the presentation really about capturing metric semantic understanding is Chimera. What is Chimera? Chimera is a real-time library for metric semantic simultaneous localization and mapping. So Chimera, in a nutshell, is taking information from a standard camera, like the one that you see here at the bottom right, and is producing as output a metric semantic 3D model. Okay, so what you see in this video is not just a flat image, it's actually a 3D model, is a 3D mesh. And of course, the geometry of the 3D mesh will describe the shape, the geometry of the environment, but also the different phases of the mesh are labeled with different colors. And these colors are not real colors, are semantic labels. For example, gray corresponds to the label for the ground, green is the label for the walls, yellow are the cubicles, light green are the chairs, and so on. So the most important bit of information probably is the fact that Chimera is actually open source, and you can take a look if you want on GitHub. You can try it for yourself. But in the next few slides, I want to just tell you, like, what are the main ingredients, what are the main modules within Chimera. So at high level, Chimera includes 3 main modules. Chimera is taking information from a standard camera, and there is Chimera VIO, which is performing visual inertial odometry. Is estimating the trajectory and odometric trajectory for the robot using visual inertial odometry. Chimera semantics takes the odometric estimate of the trajectory and builds a map around it. And finally, Chimera RPGO is going to correct the trajectory and possibly the map in response to loop closures. And we're going to look at the details of each block in a second. So let's start with Chimera visual inertial odometry, Chimera VIO. Well, Chimera VIO is in charge of estimating the odometric trajectory of the robot using visual and inertial information. You can imagine that the robot is collecting a sequence of images, and then Chimera VIO is solving an optimization problem to estimate the trajectory of the robot that you see visualized in this video, and at the same time reconstruct the 3D location of points observed in the image, which are the green points that you see here in the visualization. So in other words, Chimera VIO is a keyframe-based visual inertial odometry approach, which is based on GTSAM. GTSAM is a very popular library for SLAM and for optimization and robotics, and builds on top of this IMU pre-integration theory that we have proposed, back in 2015 or so. So after we have Chimera VIO, we essentially have a trajectory estimate, an odometric trajectory estimate for the robot. And we can pass this estimate to Chimera semantics, which around this estimate is going to build a 3D mesh reconstruction. So the 3D mesh reconstruction is based on a volumetric, on a voxel-based model. And the geometry of this voxel-based model is reconstructed by VoxBlocks, which is an excellent library from ETH. You can imagine that the camera is measuring distances. For example, you have a stereo camera, which is measuring distances. And these distances are integrated in a voxel-based representation using VoxBlocks. At the same time, what we do on top of that is also to label, to estimate a semantic label for each voxel using Bayesian updates in 3D and using a raycasting approach. Of course, once you have voxel-based representation, it's quite easy to convert a voxel-based representation into a 3D mesh using standard algorithms such as marching cubes, for example. So the thing that really stands out about Chimera semantics is that while most of the pipeline to reconstruct this kind of maps run in GPU, Chimera semantics is fully CPU-based and it's running in real time, can run at 10 Hertz on a standard laptop, which is quite important because it means that you can easily run this on your robot without investing too much computation. So the next module is Chimera Robust Postgraph Optimization, RPGO. And the basic idea is that if you look just at the odometric trajectory of the robot, which is the one that you see in red, by definition, odometry is going to drift over time. It's going to accumulate error over time. But what happens is that the robot at some poses may reobserve the same portion of the environment. For example, this pose here and this pose here can observe the same part of the environment. And then the robot can use that information to correct the trajectory. This is what is called a loop closure in robotics or SLAM. So in other words, imagine that these two poses are observing a similar portion of the environment. We can compute a loop closure, and we can use this loop closure, which I'm visualizing as a dashed line, to correct the trajectory. Again, this is the odometric trajectory, and this is the improved correct trajectory after loop closures. So in Chimera RPGO, we use a standard technique to detect loop closures. We use a standard bag of words technique based on ORB descriptors. But what really stands out is that we have an outlier rejection approach to reject bad loop closures. It's very common in this problem to have bad loop closures resulting from incorrect place recognition. And Chimera is able to reject this bad loop closure using PCM, which is an approach from the original version of Chimera was using PCM, which is an excellent approach from Josh Mengelson. But more recently, we're adopting graduated non-convexity, which is one of the algorithms I'm going to mention later in this presentation. So why is it important to reject bad loop closures? Well, if you do not have outlier rejection, if you don't reject bad loop closures, what happens is that you have the trajectory of the robot in red, and in response to these blue loop closures, many of which are incorrect, essentially this bad loop closure will completely distort the geometry of the trajectory. On the other hand, if you have some outlier rejection, if we reject these bad loop closures, we kind of select only the good loop closures in blue. And the result is that we have a nice trajectory, which is smooth and is also globally correct. So in other words, outlier rejection for loop closures in postgraph optimization is a key ingredient to get an accurate trajectory. So I also want to mention one last block, which is the PGMO block, which is the postgraph and mesh optimization block, which is kind of an extension of the postgraph optimization approach. Well, what happened is that in the original proposal for Chimera, we were just doing postgraph optimization. So in response to loop closures, we were able to correct the trajectory of the robot. Imagine that the trajectory of the robot is the one in red. In response to a loop closure, we were able to correct this trajectory. But in the original release of Chimera, we are not correcting the mesh, which means that the mesh was actually drifting over time. While the trajectory was correct, the mesh was drifting over time. And so over the last several months, we presented a joint approach to correct at the same time the trajectory of the robot and the 3D mesh of the environment, which I'm visualizing here in a kind of a simplified way. And the approach is summarizing this journal paper, which is a very nice paper. It's comprehensive about the work we are doing on Chimera. And the approach is based on the idea of deformation graphs, which is an old idea in computer graphics, which was used a lot for animations, like in 3D computer graphics. And I just want to tell you a high level, what this is about. So imagine that I want to correct in response to loop closure both the trajectory and the mesh. Of course, I cannot directly optimize or correct the mesh because the mesh will be a huge object, will be like millions of vertices, right? So in the deformation graph, what you do is you subsample the mesh into a smaller set of vertices, but to each vertex, you also associate a local reference frame, which is the one that I'm showing in violet here as a violet triangle. And what you do, you have a local reference frame attached to different vertices of the mesh, and you have, of course, a local pose attached to the trajectory, to the poses along the trajectory of the robot. And out of this collection of poses, you build a graph with edges connecting either consecutive poses or connecting nearby vertices in the mesh, or connecting the mesh to the robot poses observing the mesh. So this is what is called a deformation graph. After you have a deformation graph, imagine that the robot gets a loop closure, for example, the one in blue. Well, after you build a deformation graph, you can essentially formulate an optimization problem which, in response to loop closure, is able to deform at the same time the trajectory of the robot in red and the mesh in violet. And as a result, you will have a globally consistent 3D mesh as well as a globally consistent trajectory. It's a nice approach. It's not even too much computationally expensive. And something nice that we show in the paper is that, by the way, after you do some manipulation of the math, mathematically, this problem of postgraph and mesh optimization is equivalent to standard postgraph optimization in robotics, which is a very well understood problem in SLAM. So you can just use GTSM and off-the-shelf tools for optimization. So let me just give you what is the result of this. Let me just show you what is the result of this. Imagine that you have a robot. That's a top view map top view version of the map reconstructed by the robot. The robot is starting here, is navigating around, is building a map, and eventually comes back to do a loop closure. And you can see that when the loop closure finally happens, the robot essentially can deform not only its trajectory, but also the entire mesh, and can propagate the correction from the loop closure to the entire mesh. You see that the mesh gets globally corrected in response to loop closure. And the result, of course, is that you get a much more accurate 3D reconstruction. For example, on the right here, I'm showing the 3D reconstruction color-coded by mapping errors on standard dataset. This is the Europe dataset. So before we do the post-graph and mesh optimization, we have quite large errors. And after we do the deformation with the post-graph and mesh optimization approach, we just reduce the error across the map. Okay, so let me conclude this part about Chimera. So Chimera, in a nutshell, is a library for metric semantic reconstruction. And the features that really stand out from Chimera are the robustness to incorrect loop closure. We have multiple layers of robustness to incorrect loop closures. And we have this unique approach, which is doing post-graph and mesh optimization to essentially keep a globally consistent metric semantic map of the environment. Moreover, Chimera runs in real time on a CPU, thanks to multi-threading. And we also tested we have real-time performance also on embedded computers, such as the NVIDIA TX2 embedded computer. We've been testing Chimera on multiple data sets from simulated and to real data sets, hand-held sensors, benchmarking data sets, self-driving application, real robots, and so on. And probably the most important bit is that we are planning a release 2.0 of Chimera in spring 2022. So stay tuned.
Luca, a quick question, if I may.
Yes,
go
ahead.
This concept also does it apply also to to occupancy grids, like the classical ones, before you go to mesh optimization?
No, the mesh is really the key. Unfortunately, you might do something in the occupancy grid case, but the fact that you are confined to this discretization of space makes it more complicated. You cannot directly extend it. So this kind of deformation graph was really proposed to do animations, to interact with a 3D model and to move around the 3D model in 3D. And I think it easily extends to 3D point clouds. It easily extends to, applies to meshes, but for voxel-based representation, I think it's trickier. So, and the nice thing with meshes is that, again, we define the geometry of the mesh, but for each phase, we still have the semantic labels. So essentially, we can deform both the metric part and the semantic map at the same time. There is much more to say, Vadim, also because the volumetric map, in my opinion, is not a really scalable solution. So actually, we are trying to get rid as much as we can of the voxel-based map in favor of the mesh-based reconstruction.
Sure. Just to verify, the semantics layers, are they coupled with the mesh? Is estimation problem, or are they just two separate problems?
The semantics, you can think about just attributes of the mesh. So what you really deform is the 3D location of the vertices of the mesh, and then the semantics comes for free.
Okay, cool. Thanks.
All right, thanks. Great questions. Okay, the second part of this talk is about taking a step further towards high-level understanding and presenting this idea of 3D dynamic scene graphs, which of course are going to build on top of Chimera. So what is a 3D dynamic scene graph? Well, a 3D dynamic scene graph is just a new map representation, is a new mental model for robots. And what I want to do here is to just guide you through this video. This is a 3D dynamic scene graph. And then together we are going to read the text on the right. So what you see here is a 3D dynamic scene graph, is essentially a hierarchical representation of the environment in which you represent the environment as a graph with multiple layers. So at the lowest layer, you have the metric semantic mesh, which is exactly the one we are building with Chimera. But as you go up in the layers, you are abstracting low-level information into higher level semantics. So for example, you're abstracting the mesh into objects and agents, into rooms, into buildings, and the more you go up, the more you go towards high-level semantics. So again, this is a graph. So not only we are going to have nodes in the graph, but we are also going to have edges in the graph. For example, the edges can capture the fact that an object is grounded to a specific location in the mesh, or maybe an object belongs to a specific room, or maybe the room belongs to a specific building. So most of the layers are kind of easy to understand. Buildings, rooms, objects, and agents, we understand what these are. What is a bit more mysterious is the layer of places and structures, but it's still quite easy. Structures are just the walls, the ceiling, the ground, like this kind of structure in the environment, while places are obstacle-free locations the robot can travel to. You can imagine the graph of places as being a topological map of the environment, what people in robotics are calling a topological map of the environment. So more formally, a 3D dynamic scene graph is a directed graph where nodes are spatial concepts. Anything that really lives in 3D is a spatial concept. And edges represent spatio-temporal relations between concepts. For example, we can say that the agent I is in room J at time t using an edge within the corresponding nodes. So what are the key insights? Why do we believe that this is a very powerful model? Well, first of all, we started saying that capturing relations in 3D is very important for humans and for robots as well. But finally, this model, as a graphical model, can easily capture relation between concepts, right? We have edges connecting different concepts in the graph. Moreover, this representation is unifying a number of map representations in robotics, right? So if you look at the lowest layer, we have a metric map, we have a landmark-based map in layer 2, right? We capture objects and so on. We have a topological map, and all these maps are connected through edges. So essentially, this is a unifying representation for metric and topological mapping in robotics. It is also an actionable representation in the sense that finally we have understanding of rooms, objects, and so on, and we can provide high-level instructions to our robot. Finally, we can tell our robot, if we are able to build this representation, we can finally tell our robot, reach out this object or go to this specific room. The robot will be able to understand these instructions. And of course, other nice things, the representation can also capture dynamic agents, dynamic, humans essentially in the scene. Of course, most of the work we've done is not only just proposing the representation, but also designing algorithms that can build this kind of scene graph, 3D scene graphs from sensor data. And we're calling these algorithms spatial perception engines because essentially these algorithms are doing much more than traditional SLAM, and they are inferring this kind of 3D dynamic scene graphs from sensor data collected by the robot. I'm going to comment on the fact that these algorithms are not real-time yet, but we're working towards that goal. Okay, so next few slides are about telling you, just few bits about how we build the different layers of the dynamic scene graph. Well, the metric semantic mesh layer is, again, is pretty much the output of Chimera. So you have seen about this in the previous part of the presentation. The only extra cleverness, the only extra care we have to use here is that we care about doing mapping and 3D reconstruction in very dynamic environments. So with the standard version of Chimera, if you had a human working in front of the camera, that resulted in artifacts being constructed as part of the mesh. So in the new version of Chimera, what we do is that we use the semantic information of this being a human to avoid including the corresponding depth measurements into the map. So essentially, we reconstruct only the static portion of the map without reconstructing dynamic elements as part of the 3D mesh. And this is a process that we call dynamic masking. The second layer, which is one of my favorites, is the layer reconstructing or estimating the poses of objects and agents. And let me start by telling what we do about the agents. So for the agents, we combined a state-of-the-art algorithm for human pose shape estimation from the group of Kostas Danilidis. So imagine that this technique is taking an image of a human and is reconstructing in real time using a deep graph neural network, is reconstructing a 3D mesh of the human being pictured in the image. And then what we do on top of that is to do some model-based tracking of the human using, again, post-graph optimization. As a result of that, we are able to do this kind of dense tracking of the humans moving in front of the camera. And we have a very dense model, very dense mesh for the human. And we can also track the trajectory of the humans over time. And this can easily run in real time. The second part is about estimating constellation of objects in the environment. And we kind of distinguish objects for which we do not have a shape prior against objects for which we have some CAD model, we have some shape information about the object itself. In the case in which we do not have shape prior, we don't do anything fancy, we just do some Euclidean clustering and we compute a bounding box. So remember that we have a metric semantic mesh. So the semantic labels are already in the mesh. We just break the mesh into different objects and we fit bounding boxes to the different objects. Instead, when we have some shape information about the object, we do something a little bit more sophisticated. We use what is called teaser++, which is one of the certifiable algorithms I'm going to talk about in the last part of the presentation, if time allows. And as a result of that, we can extract a number of objects from the metric semantic mesh. When it comes to places and structures, again, the places are just sorry about that. So let's see. The places are just a topological map of the environment. So what you see in red here is quite dense of a graph in which each node of the graph is an obstacle-free location, and edges between two nodes are telling that there is a traversable path, there is a collision-free path between the two nodes. So it's really a topological map in robotics. And with a standard library to just estimate this map, you can think about it as a skeleton of the environment. But what we do on top of that, if my computer allows, we are also clustering the map into different rooms. And in a nutshell, what we do is that we use the voxel-based representation to detect the walls between rooms. And we use this information about the walls between rooms to inform a graph clustering algorithm, which is separating, again, the graph of places into the different rooms in the environment. And finally, there is the layer 5, which is buildings. So far, we have been mostly doing single building reconstruction. So at this layer, we don't do really anything. We just put an extra node, which is the building node at the top, and we connect all the rooms to this building node. But I still want to take advantage of this slide to show a little bit more in detail some of the layers of the dynamic scene graphs. And in particular, you can see layer 2, in which you have the objects and the humans in the environment. I also want to take advantage of this slide to mention that currently algorithms to reconstruct 3D dynamic scene graphs are offline. They're taking around 30 minutes to reconstruct, but they're fully automatic. Okay, so
can I interrupt with a question about this structure? So you showed us in layer 2 that you form an understanding of the objects that are in the scene. What about, and you said that these are the nodes in your graph. What about the edges? How do you kind of understand the existing of an edge between two objects? And also another question, sorry, if that's okay. Would this framework be only suitable to work in buildings, with rooms, etc., or is this generalizable to kind of other kinds of environments?
Fantastic questions. Thank you so much. These are great questions. So whatever you see in this picture, these are all nodes, right? There will be nodes for the rooms. Each place is going to be a different node. So there are going to be many places nodes. There are many object nodes, and even the vertices of the mesh end up being nodes in the scene graph. Regarding to edges, what we stress in the paper is that there is no single recipe. You can assign, depending on your application, you can model the relations you care about, and you can also model the attributes for each node that you care about. We explore very simple things. In the paper, we explore very simple things. For example, for each object, first of all, the edges are not super visible. That's a byproduct of the visualization. But for each object, right now we're just associating the nearest place, the closest place in the graph. And for each place, we're just collecting, of course, which room the place belongs to. For other application, we're just connecting objects which are within some distance, but you can be really creative about that. You can try to capture maybe kind of interactions. You can capture, an edge can capture the fact that a human is trying to grasp an object. You can really be creative about that. And this is what we say, in the paper, and that's something that we strongly believe in.
You're currently relying on the specification, right? By the user. You're currently relying on specification.
Yes. Mm-hmm. I think you can easily do some learning on that. You can use, and something that we started doing as well, you can do some graph neural networks to start reasoning over the relations among objects and so on. but there is definitely much more work to do. Like, the original version, which is the one I'm describing today, is mostly like, kind of hard-coded rules for the relations that you want to detect, mostly geometric relations, but there is much more you can do. My comment is also related to the second question, which is about indoor versus outdoor environments. Of course, the work I'm proposing so far is mostly about capturing indoor environments. What we strongly believe in is that it's quite easy to generalize this idea to outdoor environments. For example, the notion of objects. Imagine that instead of having an indoor environment, you're going to have, I don't know, a city block. You're going to have a urban environment. In the urban environment, the mesh will still make sense. There will definitely be objects. There will be definitely places the robot can move to. But of course, there are no rooms and buildings. In that case, instead of rooms and buildings, you would have maybe roads, you have maybe neighborhoods, right? So you will have different layers. So in a sense, I think my general answer is that you will need to tailor a little bit the type of nodes that you put in the graph and the type of edges that you put in the graph to your application. And if you do this in a modular enough approach, in a modular enough way, we can just design, we can have the layers connecting to each other in a modular way, and we can just design algorithms to create extra layers. That's really like, the vision. We're very far from that. So there is plenty of work to be done. Fantastic question. All right. I want to stress one slide because, I see a lot of potential in this idea in terms of application that we barely explored on our side, but I think there are plenty. In the applications of 3D scene graphs in general, even if they're not dynamic, like 3D scene graphs. And I'm listing all the applications. The first application is hierarchical planning. If you have a hierarchical representation, there is a lot you can do in speeding up motion planning, right? You can reason at the level of rooms instead of reasoning at the level of the mesh representation. And you can speed up really like, the motion planning process. Just as a very naive approach, a very naive example that we put in the paper, we compare doing A*, which is a standard motion planning algorithm on the voxel-based representation, against doing that on the scene graph. And just by leveraging the hierarchy of the scene graph, we can bring down the computational time of A* by a few orders of magnitude. Of course, that's a very baseline algorithm. You can do better than A*, but definitely once you have a hierarchical representation, you can simplify computation. You can take advantage of that to simplify computation. Now you can do semantic path planning, right? You can tell your robot, go to grasp this object, because the notion of objects, geometry, and so on is in the map. You can easily do human-robot interaction because these kind of models are very close to what we have in our brains, like to model indoor environments. And a number of other things. You can do long-term autonomy, visual Q&A, new navigation tasks. You can think about monitoring and robustness, prediction, and so on. And there are many, many applications of this. Beyond that, just by thinking about 3D scene graphs, I believe that new challenges come to mind. For example, after proposing the 3D scene graph idea that I presented in the last few slides, we realized that our algorithm was able to cluster the different rooms, right? So we are able to detect what are the different rooms. But we are kind of unable to say if a room is a kitchen or if a room is a bedroom, which is kind of an important information for the robot to know. So we took that as a challenge, and we decided to investigate how to do labeling of the missing nodes in the scene graph. So some nodes in the scene graph are not labeled. We investigated approaches to label the remaining nodes. And the basic idea is that there is a lot of correlation between different layers in the scene graph. So for example, imagine that the blue one is the room node, and the orange one or the yellow one are the object nodes. Essentially, as a human, if I tell you that within a room, there is a clock, there is a bed, there is a book, most likely as a human, you will be able to infer that the room is not, for sure, is not a kitchen, it's most likely a bedroom, right? So we investigate techniques based on deep learning, which are able to perform inference on the label of missing nodes in the scene graph. And unfortunately, I'm running out of time, so I will not be able to tell you too much about this. But if you're interested, we presented a graph neural network architecture to label nodes in the scene graph in this new RIPS paper, which has been presented a couple of weeks ago. Not only we do that, we also propose a new architecture, which is called neural trees, which is a new graph neural network architecture that works extremely well in practice and has also some strong theoretical guarantees. Okay, in the interest of time, I will move to the last part of the presentation in which I want to give you a high level. I'm going to switch gears, a slightly different topic. I'm going to tell you high level, what is this idea of certifiable perception algorithms? And I'm going to focus on object pose estimation. These certifiable perception algorithms are indeed the algorithms that we use to construct some of the scene graph. And they are very general class of algorithms. So to tell you what is a certifiable perception algorithm, let me just use maybe a running example just to make the discussion a little bit more grounded. So consider the following perception problem, which is image-based object pose estimation. So in image-based object pose estimation, I give you an image and ask you to compute the 3D pose of the object pictured in the image, in this case, the car pictured in the image. So a standard approach to do this kind of pose estimation works in 2 steps. In the first step, we typically use some sort of feature detection, some sort of neural network to detect features in the image. You can think about the features as being distinguishable points, for example, corresponding to the wheels, to the headlights, to the mirrors, and so on. And these are what are called semantic key points, meaning that these points will correspond to specific locations on the car, right? So the neural network is trained to detect, for example, wheels, mirrors, and so on. And then the second step is taking this feature detection and is solving some sort of estimation problem that, given a CAD model of the car that you want to detect, we try to compute the 3D pose of this CAD model in a way that fits the features that you detected. And what you see here is the reprojection of the 3D CAD model on the image. And you can see that the silhouette of the CAD model in red, in this case, is fitting very well the shape of the car. So the first part of this approach is typically what is called the perception front end, while the estimation part is called the perception back end. And while I'm using image-based object pose estimation as a running example, I want just to spend one slide telling you that this split between perception front end and back end is actually quite general. You can have a perception front end and back end in object localization in images, which is what you have seen in the previous slide. You can do the same in object localization in point clouds. You have a point cloud, you extract features, and then you fit your object to the features. And even in approaches which are completely different, such as SLAM, typically you're going to have a front end which is detecting features from the sensor data, and then you have some sort of optimization or estimation problem, which from the features is trying to estimate the states that you care about. And the algorithms I'm going to discuss are going to apply to all these problems. So what is the problem that, why these algorithms, like, these perception algorithms may fail in practice? Well, the typical issue is that you have an image, you're calling the state-of-the-art neural network to do feature detection in this image, and the neural network will detect some good features. For example, the one in green are good detections, and these are what we call the inliers. But at the same time, the neural network can detect a large number of outliers. These are features that do not belong to the car, or maybe they're just misdetected, right? So the red features are kind of uninformative for the detection of the car. And issue number one is that the front end, even with the state-of-the-art deep learning-based approach, can produce many, many misdetections. It's not uncommon to have 90% of the measurements being misdetections. The second issue is that if you're passing too many outliers to the backend, to the estimation block in the backend, the estimation block will just give up. It will not be able to produce a reasonable estimate. For example, in this case, the algorithm thinks that the car is the yellow one, and as a human, as humans, we see that that's incorrect. So again, issue number two is that the backend may fail if there are too many outliers. While a lot of researchers in the community are trying to improve the feature detection part, we really wanted to push the boundary of performance of robust estimation of the perception backend. So we wanted to design new estimation modules which are robust to extreme numbers of outliers. And I'm going to tell you a little bit more in the next few slides. First of all, the nice thing is that despite the variety of applications that I mentioned, right, from SLAM to object pose estimation, in the back end of all these applications, typically you're just solving an optimization problem. You're solving an optimization problem in which you want to estimate some variable x. For example, you want to estimate the pose of the car, given a number of measurements y. The measurements, for example, can be the features that you detected in the image. And you compute the x by minimizing what is called the residual error. The residual error informally is just measuring how well the x is fitting the y, each measurement y. And of course, you're going to have many, many measurements. In practice, you don't use a squared norm, but you typically use a robust loss function to gain robustness for outliers. That is what people in robust estimation from the 80s told us to do. But the question is, well, we have a robust loss function, right? People in robust estimation told us how to get robustness to outliers. So why this is not robust to outliers? Why if we solve this optimization problem, we don't get an estimate which is robust to outliers? Well, it turns out that the problem is not the formulation that we have, is how we solve this optimization problem. What happens in practice is that typical choices of the robust function rho are non-convex. Non-convex is the function that I'm showing here. And as a result, if you plug this choice of rho in your optimization problem, you are going to get a cost function that you want to minimize, which again is non-convex. For those of you who are not familiar with optimization, non-convex means that you have a cost function with multiple valleys, multiple minima, and these are extremely difficult to optimize. First of all, I'm visualizing just a 1D example, just for simplicity, but these problems are quite high dimensional. And non-convexity means that if you're getting to the bottom of this cost function, you get a nice and robust estimate. But if you get stuck in what is called a local minima, essentially you get a bad estimate for the quantity you're interested in. And just to summarize in a couple of sentences, what is the state of the art? Well, the state of the art is either based on local solvers, which will start from an initial guess and will go downhill towards a minima. For example, you can think about gradient descent as an example of that. But local solver can be easily stuck in local minima, so can be easily producing this kind of incorrect reconstructions. An alternative is Ransack, which can be understood as optimizing this cost function using a sampling-based approach. Unfortunately, Ransack is a very popular algorithm, is a great algorithm, but mostly applies to low-dimensional problems. Can be still seen failing with high probability if you have too many outliers, and is non-deterministic, which in some problems can be an issue. The other issue is that both type of algorithms at the state of the art will fail without notice, meaning that they will return an estimate. The estimate can be completely wrong, but these algorithms will not be able to realize if the estimate is correct or wrong. So a lot of the research we are doing, and this is the notion of certifiable perception algorithm, is about computing globally optimal solutions to these optimization problems, and being able to have a certification approach which is telling us whether the estimate that we got is the correct one, is the optimal one, or is not. And I will just do a one slide overview of the work we've been doing. Typically give much longer presentation just about this. But the basic idea is that you can frame several perception problems in robotics under the lens of this kind of optimization problems, which are, again, robust estimation problems. And what we have developed is a toolbox of algorithms which are able to solve to optimality this kind of optimization problem. The toolbox of algorithms, quite a lot of stuff to say here, but we have a graph theoretic way to reject gross outliers even before solving the problem. Then we have an approach which is called graduated non-convexity, which is an approach to solve a heuristic to solve this optimization problem. And I'm going to show something about this in the next slide. And then we have a certification routine based on convex relaxations, which are able to either certify that we got the optimal solution on these problems, or just reject the solution as suboptimal. So it's kind of judging the quality of the solution. So if you want just to have more pointers about this is something that we've been working on over the last 3 or 4 years. You can look at the corresponding pointers. And in the next few slides, really, I just want to tell you a bit more about graduated non-convexity. And then I just want to give you an example before closing. So graduated non-convexity is a popular algorithm to solve non-convex optimization problems. The basic idea is that you have a non-convex problem that you want to solve, and graduated non-convexity is going to tell you, look, non-convex optimization is hard. Don't try to solve this optimization problem. start by solving a much simpler problem. Start by solving a convex approximation of the problem. You can solve that. And then at each iteration of the algorithm, you increase a bit the amount of non-convexity and use the previous estimate as initial guess for the current iteration. You keep increasing the amount of non-convexity, you optimize starting from that initial guess, and eventually, after you increase all the way, like, the non-convexity, you recover the original cost function. So the only thing that you need here is really a parameterization of the cost function with a parameter mu that can increase or decrease the amount of non-convexity. And we show in the paper how to define this kind of what are called surrogate cost functions, which are convex for some choice of mu, and then becomes like a non-convex as you increase the mu. So something that is kind of important to say here is that graduated non-convexity is something that we didn't invent, something that we haven't invented. Graduated non-convexity is a very standard approach from computer vision from the 90s, going back to Blake and Zisserman and Black and Ragarajan, but was used in a very different application. It was used for surface reconstruction in early computer vision. For some reason, didn't get a lot of traction, in the early days. What we did is to rediscover this technique, understand that this technique is indeed explaining some of the state-of-the-art approaches for outlier rejection, for example, in SLAM, and also showing that graduated non-convexity is a very general and powerful framework for outlier rejection in robust estimation problems, such as 3D pose estimation for objects or even SLAM. I have another visualization of graduated non-convexity, this time in 2D, just for fun. You see that this is the function we want to optimize. And then we just start from a convex approximation and we increase the non-convexity as we go. Okay, so I will probably just give you the high-level picture, a little bit more details, but I still want to make sure we have enough time for questions. So what we have done over the last few years is to just show how to apply this toolbox of certifiable perception algorithms to many problems in perception. We started with object pose estimation in point clouds. So we have a point cloud and we have to estimate the pose of an object, for example, a serial box. And we propose teaser++, which is an example of certifiable algorithm, which is robust to an impressive amount of outliers. We can estimate correct poses, even in the presence of 95% of outliers. And teaser++ is running in real time, and we also have an open source implementation on GitHub. We then move to object pose and shape estimation, in which at the same time we have to estimate the pose of the object, but also what is the shape of the object. And we propose what is called shape sharp, which is an algorithm to estimate from images the pose and shape of the object. This is also robust to outliers, but the original proposal was running offline. And more recently, we proposed the last algorithm, which is again about pose and shape estimation, but this time from point clouds. The corresponding algorithm is called pace sharp, is robust to an impressive amount of outliers. This time it runs in real time and was best paper finalist at RSS this year. So maybe in a couple of minutes, I want just to give you the flavor of what is the last approach, which is pace sharp, and then I will conclude the presentation. So in pace sharp, again, we're given an image and also a point cloud of the environment. And the goal is to estimate the pose of an object and also estimate its shape. We do not estimate the shape from scratch. We're given a library of potential shapes, for example, of potential cars. So we have at the same time to understand what is the car we're looking at and what is the pose of the car. And the way the approach works is that there is a feature detection stage. Again, this is based on some standard neural network. We have a graph theoretic outlier pruning, in which we say, for example, that some of the features are incompatible with each other, right? If this wheel and this wheel are 20 meters away, they're unlikely to belong to the same car. So we do some graph theoretic reasoning to reject this kind of gross outliers. And then we use graduated non-convexity to compute an estimate of the pose and shape of the car. So there is much more to say, but actually I will directly jump to the results just to show one last slide about the results, which I believe are particularly exciting. This is a result of, again, this certifiable algorithm on a self-driving data set in which you want to do vehicle pose and shape estimation. So you see the video, you see that we have the features, which are the ones in red, and you see the shape of the cars, which are the poses computing from pace sharp. And the thing that is exciting, I believe, is that if you look at the quantitative results here, so the results, the numbers can be understood as success rate. So the higher, the better. And we're comparing deep learning, state-of-the-art deep learning approaches over the last few years against PaceSharp, which is the proposed approach. And in most of the performance metrics, essentially we can be state-of-the-art. We still use deep learning, of course, for the feature detection, but just by using this optimization-based approach, we can beat state-of-the-art approaches from deep learning. And the other good news is that PaceSharp is running overall in half a second in a non-optimized Python implementation, meaning that if you implement this in C++, you can easily get something that is running in milliseconds. Okay, so we conclude here saying that the point of this presentation is that there is still a large gap separating robot and human perception. And my point was that we need to go beyond SLAM and think about real-time 3D high-level understanding. In this presentation, I told you about a few efforts in this direction, told you about Chimera, which is a real-time open source metric semantic SLAM library. And I also mentioned this cool idea of Postgraph and mesh optimization. What I didn't mention is that we also have a multi-robot extension of Chimera, which is called Chimera Multi, just been accepted on the transactional robotics. Then I mentioned the idea of 3D dynamic scene graph, which is an expressive and general representation for robot perception and spatial AI. I mentioned about this idea of having new applications for scene graphs, and also just mentioned the notion of neural tree. And finally, I concluded by presenting the idea of certifiable perception algorithms, which are a broad class, which is a broadly applicable framework for robust estimation, robust geometric perception, which is applicable from object pose and shape estimation to SLAM. And the latest work in this direction, one of the latest works is this work on category level perception, which was a best paper finalist at RSS this year. So I will conclude here just by thanking the students for doing really the heavy lifting behind these slides, thanking the sponsors supporting these slides and this work in general, and just thanking you for your attention. And if you have a couple of minutes, I would be delighted to take a few questions, if there are any.
Luca, thanks very much. It was very, very interesting. Thank you very much. All right. Any questions from the audience? Now's the time. Any questions? So maybe I'll ask in the meantime. So Luca, in the last part, maybe you showed that you basically base your system on some set of given CAD models, right? What happens? Are you able to detect the situation when none of these CAD models actually fits the the object that you actually observe, or can manipulate it such that it actually fits?
Yes and no. Yes, because a posteriori, you can still do that. After you compute with these estimation algorithms, you compute essentially the optimal pose and shape of the object you're looking at. Then you can compare this solution against the dense point cloud, for example, right? You have a dense point cloud, you can see how this dense point cloud is fitting the optimal solution that you computed. No, in the sense that I believe we have to do a little bit more in the following sense. Right now, the split between front end and back end is something that is very common, but it's also creating a little bit of a bottleneck, because what happens is that even if you have perfect algorithms for the back end, and now we have very powerful algorithms for the back end, if the front end is producing complete garbage, we're still doomed to fail in a sense, and we're still doomed to compute some meaningless estimate, even if there is a vehicle we are looking at. So shorter answer, I think we can do heuristics to check if the 3D construction still makes sense. But in the future, what we are envisioning is a little bit of a tighter coupling between the front end and back end to really take full advantage of the robustness of the algorithms we are proposing. We are thinking more about we have a paper last CVPR about this. We're thinking more about the back end kind of self-supervising the front end to improve the detection performance.
That's cool.
Good question.
Yeah, that's cool. All right.
I have another question, if that's okay. Luca, you said that you were working on extensions of the two. Can you go back to your slide? The first framework that you showed that's about the scene detections, and you said that that's already extended to multi-agents, and also, I mean, the previous one, your summary slide, just to make sure.
Yeah, I actually wanted to show you. Yeah, let me go to the extension. I also have a couple of slides about the multi-robot.
I'm very interested in understanding the extensions of the two first components, right? The pose estimation, how do you account for other agents in the environment? And also in this scene graph, what is the meaning of the fact that there is more than one agent?
Yeah, so these, I have a couple of slides. I love this work. It's a collaboration with John Howe at MIT. I typically do not have much time to discuss, but this is the case in which we do multi-robot chimera. So in this case, what you're looking at is a 3D reconstruction of the map, which gets created by multiple robots. And what really changes is that now you can start doing loop closures between different robots. So when the robots are meeting each other, can exchange information and can correct their trajectories after they meet. And they can still kind of reconstruct this metric semantic model of the environment. What is really distinctive of this setup is that we propose a distributed approach. What happens in a multi-robot system is that it's not practical to share all the sensor data among the robots. It's just too much information. So in a distributed approach, what you do is that you have each robot doing its own map, and then the robots are exchanging just a little bit of information to kind of reach consensus on how the trajectories, on how their trajectories look like. And after doing that, they can correct the local mesh using this mesh deformation approach. So huge amount of details there, but really the thing that is distinctive is that you can no longer pass information around. You have to be more clever about the communication. But something that I really love about this multi-robot work is that is really showcasing how powerful, for example, is the post-graph and mesh optimization approach. So here you see a real test that we've been doing, I think, last May. This is just a post-graph. You see the trajectory of the robots. The trajectory gets corrected when there are loop closures. And you can see that eventually, actually, the trajectory estimate fits very well with the map, the satellite map. I think the second part of the video is even cooler. This is showing the kind of the post-graph and mesh optimization part, in which the robots are estimating a local mesh and their trajectories. And you see that as soon as the robots are meeting each other or they have some loop closure opportunity, they're able to just deform that mesh and correct according to the latest measurements that they have taken, until eventually, this mesh gets better and better, and it becomes good 3D model for the environment. As you see around here, starting to get better and better. All right.
Quick question here. How tight is the coupling with semantics here? With expectation?
So on that part, there is a lot to be done. I would say that I would call what we do in Chimera a very loose coupling with the semantics. In the following sense, we reconstruct the geometry, and then we we annotate the geometry with semantics. But ideally, we would like to have a much deeper integration. We're looking at that integration, for example, in the context of scene graphs for loop closure detection, where we're trying to use more and more of the semantic information when we do some geometric estimation, for the scene graph, but it's all to be explored. And I think that's really the way. I think this is the first step, but the deeper integration is what we need to get robustness and to get better qualities of the map. And what comes to mind is also the latest work from Andrew Davison and so on. I think there is there are good ideas there to go in that direction. And maybe just to follow up on the previous question, I think the previous question from Sarah was also about the scene graph for multi-robot. We're thinking about that. It's something that will require a little bit more time to develop. For the scene graph, there is a obstacle which is even before the multi-robot, which is about getting real-time performance. What we want to do is to bring this 30 minutes compute time to build the scene graph into milliseconds. And I believe we have pretty cool ideas to do that. We're probably going to put a paper out very shortly about that. But that's the step we are taking. before going to multi-robot extensions.
Perfect.
Thank you so much. Very interesting work.
Thank you. Thanks.
All right. I think in the interest of time, we should finish now because we could have asked many more questions, obviously. So Luca, thanks again for giving this amazing talk. Thanks again. And we will see you all in the next seminar. Thanks. That's all. Thank you.
Thank you.
Bye-bye.
True pleasure. Thanks, everyone.
Bye-bye.
See you soon. Take care.
See you.